Hello everyone, myself Giri, Faculty of Home Institute for Power System subject. In this video, we are going to discuss solutions for power system questions which were asked in TSPSC AEE electrical paper. In the month of January, Telangana State Public Service Commission conducted an exam to recruit assistant executive engineers from various engineering departments. So I collected power system questions from electrical paper. Now we'll see the solutions for those questions. Let's see the first question. Now in this question, we need to match the things correctly. Now one side is mentioned reduce the Ferranti effect, improve power factor, increase power flow capacity of the line and reduce the current ripple. And other side is mentioned series capacitor, shunt reactor, shunt capacitor and series reactor. We know that the series capacitor, we'll see one by one. Series capacitor, what is the importance of series capacitor? Series capacitor, whenever you connect it to the line, it will reduce the overall reactance of the line. For example, if you have a transmission line between two buses, okay, maybe at the receiving end side you are connected a capacitor and it offers a reactance or impedance minus jXc, okay, Xc external, since it is an external capacitor. Now, what is the equivalent circuit of this? Approximately we can write like this. The line having what? Resistance, inductance, already. Now an external capacitor is added here. So that what happens? Before compensation, the line reactance is XL. After compensation, the line reactance become what now? XL minus Xc external. So the overall reactance of the line decreases because of series capacitor compensation. If overall reactance of the line decreases, what happens? Definitely system stability will be improved. Maximum power transfer capacity of the line will be improved. For example, if you neglect the resistance, what you can write Pmax or steady state stability limit of the line, the sending end voltage V1, receiving end voltage V2 by the net reactance of the line. What is the net reactance of the line? X, because I neglected the resistance, for example, just for approximation. So V1, V2 by X. What is this X now? XL minus Xc external. Now, because of the addition of series capacitor, that provides what? Minus jXc external impedance. Now, the line impedance, line inductive impedance is plus jXl. So, overall impedance, if you see in between, jXl minus jXc external. Overall reactance, XL minus Xc external. So, Xc external causes was decreasing of X. So, if X decreases, system stability will improve. Okay. So that's why the unique importance of series capacitor, if you notice, that is just to improve the stability and to increase the power flow capacity of the line. That's the beauty of series capacitor. So that means C is matching with 1. C is matching with 1. Next, shunt reactor. So the main purpose of shunt reactor is to reduce the Ferranti effect. What is Ferranti effect? Under no load condition, the receiving end voltage of the transmission line is greater than what? Sending end voltage. So to reduce the Ferranti effect, generally we use a shunt reactor. So reduce the Ferranti effect, shunt reactor. That means A is mapped to what? 2. To improve the power factor, generally we use a shunt capacitor. So that means B is mapped with what? 3. Reduce the current ripple, generally we use a series reactor. You might have studied in power electronics. So to reduce the ripples, okay, after you are converting AC to DC, generally that DC voltage having so many ripples, we connect a series reactor. And another importance of series reactor in power system is to reduce the magnitude of the fault current. Okay, so to reduce the magnitude of the fault current or to reduce the current ripples, generally we use what? Series reactor. So the best answer is what here? A. Now we move on to the next question. Let us see in this question is asking to calculate what is the symmetrical breaking current. And in this question it is clearly mentioned the symmetrical breaking capacity. Whatever the MVA rating of the breaker is given, no, that is by default symmetrical breaking capacity. And the rated line voltage also given, right? It's a 3-phase 33 kV oil circuit breaker is rated 1500 ampere. This 1500 ampere is nothing but continuous current rating of the breaker. It is a continuous current rating of the breaker. It's not a breaking current. Okay. Now this 2000 MVA by default it's a symmetrical breaking capacity. Okay. This 2 seconds is the open time of the breaker. Now, as per the question, the symmetrical breaking capacity is given. That is 2000 MVA. 2000 MVA. But what is the formula for symmetrical braking capacity? Root 3 times the rated line voltage magnitude multiplied with what? Rated symmetrical braking current magnitude. Where ISY is the rated symmetrical braking current. Now by using this formula we can calculate easily what is ISY. The ISY is symmetrical braking capacity by root 3 into VL. From here, let's calculate what is symmetrical braking capacity. 2000 into 10 power 6 divided with root 3 into 33 kV, right? VL. 33 into 10 power 3. So that you will get it in amperes. If you want in kilo amperes, this should be taken 10 power 3. If you solve this, we get the answer as approximately 35 kilo amperes. So the option is 3. Now we'll move on to the next question. See, in this question, which of the following could be the effect of using high-speed circuit breakers in a power system? See, if you use high-speed circuit breakers, the fault will be cleared very quickly. If the fault is cleared very quickly, there are two advantages. You can avoid the damage to the equipments. At the same time, you can improve the system stability. We can avoid the loss of synchronism or loss of stability of the system. So the high-speed circuit breakers generally improves the stability and also reduce the damage to the equipments. So let's see what option is mentioned here. Reduce the system reliability. No, actually it improves the system reliability but not reduce. Improve the system stability. Yes, that is the correct one. Reduce the short circuit current. So there is no link between breaker and fault current. Actually breaker will stop the fault current by opening off its contact, but it is not going to reduce the current. Increase the short circuit current. No, these two are not the options. Even first one also not correct. So the best answer is to improve the stability only we are using high speed circuit breakers in power system. This is one method of improving a power system stability. That means by using high speed circuit breakers we can reduce the fault clearing time so that the fault clearing time is always less than the critical clearing time and the system stability is improved. So we'll move on to the next question. Let's say in a long transmission line operating under lightly loaded condition, the receiving end voltage is found to be higher than the sending end voltage. Which effect accounts for this phenomena? So just what we discussed, under low load condition and lightly loaded condition, the receiving end voltage is always greater than sending end voltage. Now this effect is generally called as Ferranti effect. It is called as what? Ferranti effect. Even we discussed to reduce this Ferranti effect, we use shunt reactors. Shunt reactor, but not series reactor. Generally, shunt reactors are used to reduce the Ferranti effect. Means the reactor is connected in shunt with the line. Suppose this is the transmission line and the reactor may be connected at the receiving end, something like this. So it is connected in shunt with the line, so we can reduce the Ferranti effect. But the present question talks about if VR greater than Vs and what the effect is called. The effect is called Ferranti effect. So the answer is 3. Now we'll move on to the next question. In this question, indirectly is asking about what is the purpose of Gauss Serial method. We know Gauss Serial method is generally used for what? Load flow analysis. For performing load flow analysis, we use Gauss method, we use Gauss Serial method, we use Noether-Raphson method, we use decoupled method, we use fast decoupled methods. Okay, so Gauss Serial method is not used for stability analysis, not used for fault analysis, not unit for unit commitment. Only used for what? Load flow analysis. Now we'll move on to the next question. In this question, if the value of complex power flow in a certain transmission line is assumed to be fixed, and if V denotes the sending end voltage of the line, then the real power loss in the line would be proportional to. It's a very common question. N number of times this question is given in the competitive exam. See, sending end voltage of the line is what? Suppose if this is the transmission line, sending end voltage is V. Okay. The complex power flowing through the line is S. The line having some resistance and what? Reactance. The current flowing through the line is I. So loss in the line. Loss in the line means what? Always three-phase loss. The power loss in the line, what is the formula? Power loss formula 3 into magnitude of that I square into resistance of the line. Now what is the relation between I and S and V? So magnitude of I equal to what now? Magnitude of S by root 3 times V. Root 3 times magnitude of V. So if you substitute here, what is the power loss equation? The power loss equation is simply magnitude of S square into V square. Sorry, magnitude of S square by V square, and root 3 square is 3 get cancelled into R. If you see, resistance is constant and S is constant, the power loss is inversely proportional to V square. That means power loss is directly proportional to what now? V power minus 2. So the option is what? Inversely proportional to V square. Otherwise, when it comes to the numerator, directly proportional to V power minus 2. So the best answer is 1. So power loss is inversely proportional to square of the voltage. Clear? Now we'll move on to the next question. It is actually a basic question. You can say this is a question from three-phase circuits. A balance of three-phase supply feeds power to a balance of three-phase RL load. Under this condition, the total instantaneous power supplied by the load would be, see, the instantaneous power we can write P of T, right? What is the P of T? VR of T into IR of T plus Vy of T into Iy of T plus Vb of T into Ib of T. Since it is a three-phase system, instantaneous power in R phase, instantaneous power in Y phase, instantaneous power in B phase. If you add that, we will get a three-phase instantaneous power. Clear? But what is Vr of T? We can write like this now. Vr of T is what? For example, if you take Vm sin omega T, sin omega T. Okay, now tell me, what is IR of T? If that is the case, Im sin omega T minus pi. Why I am saying it's a minus pi? Since it is an RL load, impedance angle is what? Positive. Okay, voltage by impedance is the current, right? Impedance angle positive, that positive angle coming to the numerator means it will become what? Negative angle. So, sin omega T minus pi. Okay, so like this, we can write Vy of T and Vb of T. What is Vy of T? Vm sin omega T minus 120. IR of T is what? Iy of T is what now? Im sin omega T minus pi minus 120. Similarly, what is Vb of T? Vm sin omega T plus 120. And Ib of T, Im sin omega T minus pi plus 120. Now, you multiply this and if you solve, and finally, we'll get the answer like this. P of T will get the answer like this. You can check that. You can cross verify. We'll get a 3 by 2 into Vm Im cos pi. You may also say 3 into Vrms Irms cos pi. See, what is this power? If you see, this is nothing but active power. So, there are few conclusions I can write from here. The instantaneous power drawn by a three-phase load is always constant, and that represents active power. It is not pulsating at all. But a single-phase load, we will get different conclusions. You can try. The instantaneous power drawn by a single-phase load is what? Pulsating with what? Non-zero average. But it is always what? A constant value, and that represents active power drawn by the RL load. So, the answer of this question is constant. Since it is an RL load, draw some active power. Same question, if it is mentioned that it's a purely inductive load, then the answer is 0. If it is purely capacitive load, the answer is 0. If it is purely resistive load, the answer is constant. If it is a purely RC load, the answer is what again? Constant. Clear? So the instantaneous power drawn by three-phase RL load is always constant. It is not pulsating in nature. But many people confuse by seeing the word instantaneous power. Instantaneous power means P of T, that is V of T and I of T. Definitely it is a pulsating nature, but it's not pulsating nature. It is always constant. Now we'll move on to the next question. In this question, three statements are given. For a fully transposed transmission line, equal positive and negative sequence impedances. Yes, for a transmission line, if you see, Z1 equal to Z2. But Z0 is what? Greater than Z1, that is equal to Z2. Clear? This is for transmission line. And here is asking about the negative sequence impedance of a synchronous generator is usually smaller than the positive sequence impedance. This is also true. For a generator, if you notice, generally generator, zero sequence impedance is very small. Then what? Negative sequence impedance. Then what? Positive sequence impedance. That means the positive sequence impedance is greater than negative sequence impedance. But what is the statement here? the negative sequence impedance of synchronous generator is usually smaller than the positive sequence impedance. This is also correct statement. And first one also correct statement. And the third one, the negative sequence impedance of a transformer is generally much higher than the positive sequence impedance. Actually, this is not true. This is only true for transmission line. Because for a transformer, if you notice, all the sequence impedances, that means Z1, Z2 and Z0 are what? Equal. That represents only leakage impedance of the transformer, otherwise leakage reactance of the transformer. So, this is not a correct statement. So, A and B are correct. So, if you see the options, the option 2 is the correct one. Now, we'll move on to the next question. See this question. The impedance of a three-phase transmission line in ohms is given. If the line delivers 100 MVA of power at 400 kV, what would be the transmission power loss in the line? And if you notice this question, for this question actually the 104 kilowatt, but the original answer is 3 times of that. We will get an answer here 312 kilowatts. Let me explain why we get 312 kilowatt and why they given the answer is 104 kilowatt also. I will explain here. Actually, if you notice this question, maybe the examiner thought that it is a single phase line. That's why he has calculated the per phase loss. But we need to calculate 3 phase loss. This is the standard. For a 3 phase transmission line, if nothing is mentioned, just asking about transmission line losses means 3 phase power loss. If it is clearly mentioned that it is a 3 phase transmission line, then calculate the per phase losses, then you have to calculate per phase losses. But not mentioned here 3 phase loss you have to calculate or per phase loss you have to calculate. But by default, for a 3 phase transmission line, we calculate 3 phase power loss but not per phase power loss. Now let's see the question what is mentioned here. The impedance of a 3 phase, it's clearly mentioned 3 phase transmission line. It's a 3 phase line, no doubt for that. And the line is delivering 100 MVA at 400 kV, fine. What would be the transmission power loss in the line? It is nowhere mentioned that calculate the transmission power loss per phase. He has just mentioned that transmission power loss in the line. By means, we need to calculate 3 phase losses. By default, transmission losses means 3 phase losses only. So what is the power loss formula? The power loss equal to, just now we discussed, power loss equal to 3 into magnitude of the current flowing through the line into resistance of the line. What is the magnitude of the current? S by magnitude of S by root 3 times what? Magnitude of VL. Now this whole square into R. So if you solve this, what I get now? Magnitude of S square by what? Magnitude of VL square into what? Resistance. Let's substitute. What is the magnitude of S? 100 MVA. 100 into 10 power 6 whole square divided with what is the VL square? So VL square means what? 400 kV. That means 400 into 10 power 3 whole square, right? Into resistance of the line 5. Now if you solve this, we get the approximate answer as 312 kilowatts. This is in watts, okay? But if you solve this, we get 312 kilowatts, but not 104 kilowatt. Okay, clear? So if you are not taking this 3, then that will give you per phase loss. Then the answer would be 104 kilowatt. But that is not the correct answer. The correct answer is 312 kilowatt. But that option is not there in the 4 options. Okay. So, but the answer is what? 312 kilowatts. So, irrespective of your response, so the marks will be awarded to everybody for this question. Now we'll move on to the next question. Let's say in this question, 2 synchronous generators G1 and G2 rated for 200 megawatt, 400 megawatt respectively are operating in parallel and supplying a load of what? 300 megawatt. If the governors in both the machines are set to a droop of 4%, what will be the individual power supplied by each generator? Now if you notice in this question, the governor droops of both the machines are what? 4%. Okay. If the governor droops are same for both the machines, then they will share the load in proportion to their rating. Means what? The P1 divided with P2, where P1 is the power shared by unit 1, P2 is the power shared by unit 2, for example. Then that is equal to what? PR1 by PR2. Now when can I write this conclusion? If all the generators are having same percentage droop or same regulation constant. droop characteristics is also called regulation characteristics or regulation of a speed governor. Regulation of a speed governor or a droop of a speed governors are same in percentage. Careful, not in actual. In percentage they are same. Okay, then they will share the load in proportion to their rating. So what I can write, PR1 is 200 megawatt, PR2 is what, 400 megawatt. From this what I can write, it is 1 by 2. So from this what I can write, P1 equal to 0.5 times the P2. This is one equation. Another equation is what, P1 plus P2. P1 plus P2 is equal to 300. P1 plus P2 equal to 300. So now tell me, if I solve these two equations, what I get? For example, let's substitute here P1 equal to 0.5 P2. So 0.5 P2 plus P2, that is equal to 300. If I solve this, 1.5 P2 equal to 300 means P2 equal to what? 200 megawatts. If P2 is 200 megawatt, let's substitute here. What is P1? 100 megawatts. So the answer is what? P1 100 megawatt, P2 200 megawatt. Let's check. So the only option is D. P1 is 100 megawatt, P2 is 200 megawatt. Now we'll move on to the next question. See, in this question, a synchronous generator rated for 11 kV 50 MVA has a per unit impedance of 0.2 per unit on its own base. Then its impedance referred to a 22 kV 150 MVA base would be. So, if you notice this, very simply we can solve this question. He is asking what is the Z per unit nu. Z per unit nu equal to what? Z per unit old. There is a formula. Z per unit old into KVB old. KVB old by KVB new whole square into MVAB new by MVAB old. MVAB new by MVAB old. See, using this formula, we can easily solve this question. See, if you notice, what is the per unit impedance which is given? 0.2. This is the old per unit impedance. On old KVB, what is the KVB? 11. Right? And what is the new KVB? 22. Whole square into. What is the MVAB new? 150. What is the MVAB old? 50. If you solve this, what I get now? 0.2 into, here what? 1 by 2 whole square 1 by 4 into, here 150 by 50, that is 3. So 3 by 4 into 0.2, that is 0.75 into 0.2, which is so the answer for this question is 0.15 per unit. So if you notice, that is option 4. So we'll move on to the next question. If you see, in this question is asking about a buckle relay is commonly used for the protection of which of the following equipment. See, we know that the buckle relay is generally used in transformer. Generally, buckle relay protect the transformer against incipient faults, basically turn-to-turn faults, inter-turn faults, core faults, tank faults, or leakage of oil. Then the buckle relay takes care of protection of transformer. So buckle relay is basically used for what? Transformers. It is also called the pressure actuated relay. Generally it is connected inside the pipe that connects a transformer tank and conservator tank. Okay. So the main purpose of buckle relay is to protect the transformer against internal faults. Now we'll move on to the next question. Let's see, in this question, which of the following relays used for transmission line distance protection has the property of being inherently directional? See, the relay which is inherently directional and used for what? Transmission line. If you notice here, reactance relay, Moore relay, ohm relay, impedance relay, all these 4 relays are used for what? Transmission line protection only. But out of this, which relay having inherently directional? The relay which is inherently directional is always a Moore relay. Moore relay is a directional relay. It is also called voltage restrained directional relay. So it is basically a directional relay. So that's why the answer for this question is Moore relay. Now we'll move on to the next question. See, in this question, the surge impedance of a 300 km long is 300 km long overhead line is given 180 ohms. For a 150 km length, what is the surge impedance is asking. We know that the surge impedance is independent on the length of the line. Whatever may be the length of the line, the surge impedance will remain same. So that's why the answer for this question is same 180 ohms. So the option is what? because the surge impedance is independent on the length of the line. So that's why whatever may be the surge impedance of 300 km length of the line, the same surge impedance we can observe for 150 km length of the line. So the answer is 180 ohms. So now we'll move on to the next question. So in this question, is asking about which of these is responsible for developing the pressure in the working fluid cycle in a thermal power plant. So it's the fundamental question or basic question from thermal power plant. We know that the feed water pump is generally used to produce the pressure in the working fluid cycle of a thermal power plant. So the answer for this question is feed water pump. So option 4 is the correct answer. Now we'll move on to the next question. See, in this question is asking about which of the following is the purpose of harmonic restraint function in a power transformers. Generally, to protect the power transformer, we use a differential protection. But a differential protection may maloperates due to overexcited operation, and the second one is due to magnetic inrush currents. Clear? So, we need to avoid the maloperation of differential protection due to overexcited operation as well as magnetic inrush. For that purpose, we use an harmonic restraint. Generally, to avoid the maloperation of differential protection due to overexcited operation, we use a fifth harmonic restraint. We use. But to avoid the maloperation of differential protection due to magnetic inrush, we use a second harmonic restraint. So, the purpose of harmonic restraint is what? To avoid the false tripping of circuit breaker while protecting the transformers. So the answer is what? To prevent the false tripping due to magnetic inrush currents, to reduce the harmonic current in the transformer, to reduce the harmonic current in the transformer voltage, to reduce the harmonic power loss in the transformer. Actually, see, this is what related to the protection. So these three things are not coming into options. So to prevent the false tripping due to magnetic inrush, even overexcited operation. But only magnetic inrush current is mentioned here. So that is the best option. So the main purpose of harmonic restraint function in power transformer is to prevent false tripping due to magnetic inrush current. So the option 4 is the correct answer for this question. So that's it. So these are the questions which were asked in TSPSC electrical paper from power system area. I hope you answered all the questions correctly. So all the best.